少し早いんですけど、始めたいと思います。それで、コンパス、ブルーキャット、ここです。ちょっと早いんですけど、336ページからやります。それで、コンパス、ここです。それで、資料、テキストブック is here. So you can download the textbook from here. Then it is like page 50, maybe 50. $331, page 331. I think. Let me see. I'm sorry about this noise. I don't know how I can turn off the fan of my laptop. 336. Sorry, this has to be 36. So this is here. This suggests that I think we did this. Here. So what about the lowering operator? Not surprisingly, we find that A minus n produces an eigenvector whose eigenvalue is 1 unit lower. A minus n is become a ket of n minus 1. This suggests that there must be an unending sequence of eigenvalue below n. But that can't be correct. We already know that the ground state has positive energy, and because h equal h bar omega bracket n plus 1/2, the downward sequence must end. But the only possible way it can end is for there to be an eigenvector 0, such that when A minus acts on it, the result is 0. We should not confuse 0 with the 0 vector. The 0 vector is the vector whose components are all 0. The vector 0, on the other hand, is a state vector with non-zero components. The only possible way it can end is for there to be an eigenvector ket of 0 such that when A minus acts on it, the result is 0. We should not confuse ket of 0 with the 0 vector. Okay, so this is 0 vector, I think. This is 0 vector. I think this should be 0 vector, because 0 vector is a vector whose components are all 0. The vector ket of 0, on the other hand, is a state vector with non-zero components. Being the lowest energy state, ket of 0 is the ground state, and its energy is E0 equal omega h bar divided by 2. It is the eigenvector of n with an eigenvalue 0. We often say that the ground state is annihilated. The ground state is annihilated by A minus. We often say the ground state is annihilated by A minus. We often say this thing as the ground state is annihilated by minus A minus. So you see, the abstract construction of A plus, A minus, and N paid off. We still don't know how it is paid off. It allowed us to find the entire spectrum of harmonic oscillator energy levels without solving a single difficult equation. This spectrum consists of the energy values. So En goes like, actually usually we will write h bar omega here. Instead of omega h bar, we usually write h bar omega, h bar omega. Spectrum is using h bar omega as a unit. Spectrum goes like 1/2, 3/2, 5/2, da da da. This quantization of harmonic oscillator energy levels was one of the first results of quantum mechanics, and arguably the most important. Arguably. Why we say arguably. Arguably. Why? 間違いなく Definitely. Arguably. It sounds like unarguably. Shouldn't it be unarguably? Arguably doesn't mean not definitely. Arguably sounds like some argument remains. Anyway. Arguably the most important. The hydrogen atom is a wonderful example of quantum mechanics. But it is, after all, just the hydrogen atom. The harmonic oscillator, on the other hand, shows up everywhere, from crystal vibrations to electric circuits to electromagnetic waves. From crystal vibration, electric circuit, electromagnetic waves. 3 things. The list goes on. Even macroscopic oscillators, like a child on a swing, have quantized energy levels, but the presence of Planck's constant in equation 1030 means that the spacing between levels is so tiny that they are completely undetectable. The unending spectrum of positive energy levels for a harmonic oscillator is sometimes called a tower and sometimes called a ladder. It is illustrated schematically in figure 10.2. Figure 10.2. Where is it? No, next page. Back to wave functions. This exercise has amply demonstrated ampli, ampli. Sufficiently, amply, has amply demonstrated the remarkable power of operator algebras. This exercise has amply demonstrated the remarkable power of operator algebras. Sufficiently. Okay. And the operator method is indeed remarkable. The operator method is indeed remarkable. But it's also very abstract. It is useful in helping us find a wave function. Operator method is useful in helping us find wave functions, which are more concrete and easier to visualize. So wave function is more concrete and easier to visualize. Is it useful in helping us find wave functions which are more concrete and easier to visualize? Absolutely. Let's begin with the ground state. We just saw in equation 10.29 that the ground state is a unique state that is annihilated by A minus. Now, let's rewrite equation 10.29 in terms of position and momentum operators and the ground state wave function psi 0. So, I think this is a question mark. Because this is A minus and this is it's kind of, to be correct, this is like zero energy state projected on position basis. So whether this is 0 or dividing by the constant factor, you can remove this. So whether is this right or not? Okay. So ladder harmonic oscillator energy level ladder. Energy levels are evenly spaced. A plus and A minus raise and lower the energy level respectively. N has a lower limit of 0, the ground state, but no upper limit. Go up, up, up. If we now replace P with minus IH bar ddx, we get a first order differential equation that is much simpler than the second order Schrödinger equation. We obtain this. This is a simple differential equation that you can easily solve, or you can just check that ground state wave function. See, we can check this one, this guy. Yes, let me see. Let me go to whiteboard Fox. This is strange. Slow. By the way, I don't know if I have this schedule. I don't have the next time slot. Maybe I didn't put the next time slot. Okay, so where is it? Okay, this is this way. So P minus I omega x. P minus I omega x psi 0 x equals 0. P is, I put I downstairs and h bar upstairs, d dx, okay, this way. So we can see we multiply I, we just multiply. So this, let's see, we have I h bar d dx d psi 0x minus I omega psi 0x. Here I forgot x. I omega x psi 0x. Okay, this is 0. Yeah, I think it's okay. Then what we know, we find here is this one and this one is the same. So I can erase. Then d psi 0x dx equal minus h bar omega, sorry, this is h bar, this is h bar omega x psi 0 x. Yeah. I think it is the same. Size d psi 0x dx equal minus omega x divided by h bar. Okay, so we obtain this differential equation, and this is a simple differential equation that you can easily solve. Or you can just check that the ground state wave function this in equation 10-15 solves it. Shall we try? Let me see. d dx exponential minus omega 2h bar x. Is this 2h bar? 2h bar x square. This is minus h bar omega x e minus 2h bar omega x square. So this is just the same. So solved. I obtain this one. Okay. Calculating the wave functions for the excited non-ground state is even easier. We don't even have to solve any equations. Let's go up the ladder to n equal plus 1. We can do that by applying A plus to the ground state. Let's call the wave function of this new state psi 1. To avoid dragging the constant minus I divided by square root 2 omega h bar around in our calculations, we will just drop it in our definition of A plus. This only affects the numerical coefficient. The resulting equation is psi 1x is, you can see this is just A plus, and this is a zeroth ground state projected to x basis. So, and this is this, okay, and A plus is this. Factoring out the I, we get this. The hardest part of working this out is performing an easy derivative of exponential minus omega divided by 2h bar x square. Here is the result. Hardest part. It's not hard at all. Anyway, so you can see this. You apply this, so you have minus h bar, then you have minus h bar omega x exponential minus omega divided by 2h bar x square. So h bar cancel, I cancel, so you have omega x, here you have omega x, so you have 2 omega x, then you have this I here. So finally you have this. Or omega 1 x is 2I omega x psi 0 x. The only important difference between psi 0 and psi 1 is the presence of the factor x in psi 1. This has an effect. It causes the wave function of the first excited state to have a 0. It causes the wave function of the first excited state to have a 0 or node at x equals 0. This is a pattern that continues as we go up the ladder. Each successive excited state has an additional node. We can see this pattern emerge by calculating the second excited state at n equal 2. All we have to do is apply A plus again. So we apply, this is the A plus, this is A plus, and this is psi 1 x. We can see right away that the omega x term will result in omega x squares term, the minus partial x meanwhile will result in two terms because of the product rule for derivatives. One of these terms will come from the exponential producing another omega x. The other will come from taking the derivative of x. It's clear that what we will end up with is a quadratic polynomial. If we work out these derivatives, the resulting wave function is this. So this is psi 0, original psi 0. Then we have just constant term plus x squared term. And so it goes all the way up the ladder. We can see another pattern here. Each eigenfunction is a polynomial in x multiplied by each eigenfunction is a polynomial in x multiplied by Gaussian function. Because the exponential goes to zero faster than any these polynomials grows, each eigenfunction approaches zero asymptotically as x goes to plus or minus infinity. Also, because the degree of each polynomial is... Sorry, I think I forgot to place this link. Forgot to put this link to compass. I forgot to put this here. Then, sorry, this one goes to blue cat. Here. This should be okay. YouTube link. Okay, should be okay. So these polynomials grows, each eigenfunction approaches zero asymptotically as x goes to plus or minus infinity. Also, because the degree of each polynomial is 1, the degree of each polynomial is 1 greater than the degree of the previous one, each eigenfunction has one more zero than the previous one. It turns out that these zeros occur for real values of x, but that's not obvious from what we have seen. In a physical sense, the zeros seem a little weird because they are points where the moving mass will never be found, even though it's merrily whistling back and forth. I don't understand it. It turns out these zeros occur for real values of x, but that's not obvious from what we've seen. In a physical sense, the zeros seems a little weird because they are points where the moving mass will never be found. Moving mass will never be found. I don't understand. Even though it's merrily whistling back and forth. Merrily whistling back and forth. I don't understand. I'm sorry. I don't understand this point. Each successive this also explains why successive eigenfunctions alternate between being symmetric and antisymmetric. Specifically, eigenfunctions with polynomials of even degree are symmetric, while those with polynomials of odd degree are antisymmetric. The polynomials in this sequence are very well known. The polynomials in this sequence are very well known. They are called the Helmut polynomials. The ground state eigenfunctions e exponential minus omega divided by 2x squared is this there is a h bar, I think. The more correct definition, there is h bar. The ground state eigenfunctions, which appears in all of these high energy eigenfunctions, is symmetric in X. Let's see. I just want, I was wondering, Hermite polynomial. There is a Hermite polynomial and there is a Legendre polynomial. Legendre. How do you write Legendre? Legendre poly. How are they different? This is I was wondering. Connection between Hermite and Legendre polynomials. Here, this is Hermite polynomial. Hn is Hermite polynomial, and Pn is Legendre polynomial. Hermite polynomial have the following explicit expressions. On the other hand, Legendre polynomial have the following explicit expressions, which implies so complicated. What is a connection? See, this summation is the same. Summation goes from k equals 0 or m equals 0 to up to n over 2. Then one difference is 1 over 2 to the power n. And Legendre polynomial has, I'm sorry, I cannot write on this here. Legendre polynomial has this factorial. Then it's actually quite different. Okay, so maybe it's two different things. Figure 10.3 displays the eigenfunctions for several different energy levels. Each successive eigenfunction oscillates more rapidly than the one before it. This corresponds to a increase in momentum. The more rapidly the wave function oscillates, the greater the momentum of the system. At higher energy levels, the wave function also becomes more spread out. In physical terms, this means the mass is moving further from the equilibrium points and moving faster. These eigenfunctions contain another important lesson. Although they approach zero asymptotically quite rapidly, they never quite reach zero. That means there is a small but finite chance of finding the particle outside the ball that defines this potential energy function. This phenomenon, known as quantum tunneling, is completely unknown in classical physics. Okay, don't worry about tunneling. I think the exploration here is not enough. So don't worry. Don't worry. The importance of quantization. Importance of quantization. Let me continue this one next time. So I can put 342. Okay, I will